Hi, good morning, everyone. My name is Agrippina and I will be first presenter. In today's presentation, I will talk about software-defined industrial IoT-Edge, looking at offshore wind as our application. And in today's session guide, we will have two parts. And in the first one, I will do an introduction of what exactly is a data acquisition system in offshore wind. I will also talk about how we design communication, or rather resilient communication networks for this application scenario. And then at 10:20, we will have a quick 10-minute break. And then we will come back for part 2, where we will look at what are the challenges that we encounter in the network that we have talked about, and how I use the reinforcement learning to solve those challenges. Before I begin, my name is, as I said, Agrippina, and I'm in the Copernicus Institute of Sustainable Development in the Netherlands. I have worked for about half a decade in the field of telecommunication, and I'm currently taking a PhD in Utrecht University in the field of So, and yes, and I'm doing a PhD with the Energy and Resources Group at Utrecht University. And I think Gwange had introduced earlier that I am part of an EU Marie Curie project, which is called InnoCyPES. And in this project, my colleagues and I are looking at novel architectures and methodologies that will be used to improve system efficiencies for both the offshore wind and distribution grid domain. And more specifically, my work is in the data acquisition systems work package. Now, my work is supported mainly by my host institution, which is Utrecht University. And I also work with different partners, which are Ostel, EDF, and I also collaborate with TU Delft. I think most of you, if not all of you, have heard about offshore wind farms. And often when we talk about offshore wind farms, we think about how we get power from these offshore wind farms. But in my work package, we look at how are we able to monitor remotely the offshore assets that we deploy in the different parts of the world. And I hoped to use this figure to show, this is from EnergyNet, and it shows how we're able to derive both power and data from our offshore wind turbine generators. And I think I can use this to show that here we get, so here we get both power and data from our wind turbine generators, which we take to our offshore digital substation. And then we also take it, connect it to the transmission grid. And we also consider that we have a control center on the mainland. So this figure is what I use to best describe how data flows. And as you can see from here, we have the wind turbine generators where we collect our data from, and we run it through subsea fiber cables all the way to an offshore substation. And in the offshore substation, the data can be processed and we have a response go back to the wind turbine. And we can collect more data and send it to the control center that is on the mainland. So in this case, I will leave out the issue of power, but focus mostly on how data flows wind turbine. We also have cases where we send commands from the control center all the way back to the wind turbines, depending on a case-by-case matter. And this is how, this is what exactly we collect in a wind turbine generator. So we deploy tens and hundreds of sensors in the wind turbine nacelle to collect different measurements. It could be temperature, it could be humidity. We would want to determine how this wind turbine is collecting data by probably adjusting the yaw and the pitch. So we deploy a lot of sensors here. Most of them are very tiny. And these sensors are able to send data to the control center. So for this presentation, I wanted to look back at how far the data acquisition systems have come, all the way from 1960, all the way to the present. And in this, from the first to the third generation, what you can see is whatever was happening in the ICT sector was always reflected in how we designed our SCADA system. So for instance, in the first generation, that is the early 60s, late 70s, had mainframe computing. And this came about to help with improved data processing. And then in the early 80s, early 80s, we saw the advent of networking, where we had the local area network. And then in the early 90s, so the advent of the internet. So we saw that our SCADA systems could now communicate with each other over the internet. But now we're asking ourselves, do we think that this pattern will persist, where we have the different emerging technologies determining how we design our data acquisition system? So I was able to look at some of the technologies that we currently have, which the Industry 4.0 technologies, which are IoT, programmable networks, and edge computing, and a bit of virtualization. And we believe that this will inform how we design our SCADA system in the fourth and the fifth generation. And in the fifth generation, we look at mostly AI. So yeah, so our focus now is from the present all the way to 2030 and beyond. So I singled out these four technologies as the technologies that I believe will inform how we design our data acquisition system. So I will go through each technology and show you how we're able to see them fit in the data acquisition system. So now looking at this chart, where I'm able to map everything from the wind turbine generators all the way to the control center. You can see how I map the different technologies, starting from the left, you can see the different sensors that we deploy on the wind turbine generators. And this is a little bit towards the offshore substation, but we also have a bit of voltage and current sensors sitting in the wind turbines. Reason being, some wind farms don't have distribution substations. So we deploy these sensors, and then we send them to first a local data acquisition module. And the reason why we do that is because in the local data acquisition module, you could process the data and have immediate feedback go back to either the local control or to the actuators directly in the wind turbine generator. But you could also have a situation where you want to have centralized processing of the data that you collect. And that's the case where we send our data to our offshore digital substation. Now, we are seeing a trend where we are adopting more and more sensors and more IoT devices. So in the previous or the current models, what we see is we send data from the wind turbine generators, it goes to the local data acquisition module, and then it goes to the cloud. But then that approach has been criticized because we have a lot of latency, and we also tend to depend a lot on the internet service provider. And if the internet service provider has a problem, then you also have a problem transmitting the data. So in our architecture, we are proposing, why don't we then use edge computing? So with edge computing, what you do is the resources that you have on the cloud, you bring them closer to the wind farm. And what we now then see is that our substations begin to look like data centers because you will have to deploy more and more servers. So what you would previously have sent to the cloud, you process closer to the wind farm in the offshore substation. Now, this other track that you can see down here is where we have the voltage and current going to the merging units. This is the electrical network, and it's processed. I think you'll hear more about this on Thursday. And this is processed also within the digital substation, where we are seeing a conversion of the physical relays into virtualized components. And still in our architecture, you see that we not only do the processing here, but we also send some things to both the enterprise network and to the cloud. So when you send this data to the cloud and to the enterprise network, you're able to do a little bit more forecasting, predictive analytics, etc. So just to back the point that I was making about edge computing, we are seeing this body called the Alliance of IoT and Edge Computing, which I think most of the offshore wind suppliers are part of. I can see Siemens, I can see SAP. Yeah, I think Aruba is also quite important because they provide, there's also Schneider. So all these partners are contributing towards developing different models to implement edge computing platform in offshore wind. So we believe that this will be implemented in the wind farms of tomorrow. So the question you might ask is, why would an offshore wind farm operator be interested in deploying these technologies in their offshore wind farm? So the first reason is an offshore wind farm operator is always interested in improving operational efficiency. And as I also mentioned, is that we have, they're using a lot of data analytics for forecasting and predictive analytics. And also we would want to have more scalable and flexible data acquisition systems. As is the case with everyone, we are always looking for a way to cut costs. And last but not least, to have interoperability and standardization. So now look into the future and assume that we are already in the future now, and we already have these systems running. So as telecommunication engineers, the question we ask is, can the current communication technologies and setups that we have be able to sustain the technologies that we proposed? So one thing I probably did not mention is the fact that we have we have sensors right now doesn't mean that we cannot continue to deploy more and more. So we find that whenever we have a new business objective, we end up deploying more and more sensors, more and more IoT devices to improve operational efficiency. So we anticipate that at some point, we will have a lot of data flowing through our communication network. What that does is that it, first of all, tests the resilience of our communication networks. And also, it calls on us to ensure that if we have challenges with our communication networks, then we should have better methods to deal with these challenges to ensure that our networks remain resilient to support this data traffic. So as I'd mentioned in the previous figure, here between these wind turbine generators and the digital substation, as you'd seen in the previous figure, we have fiber cables that run under subsea fiber cables, so they run under the water, and they transmit data from these wind turbine generators to the digital substation. But from the digital substation, we also have another connection which we call the wide area network that allows us to communicate with the cloud through an internet service provider. And we can have another cable that also runs under the sea, which we call an export cable that sends data to the enterprise network, which is on the mainland. So my research work primarily looks at how can we design, validate, and test how well we build the communication at this point and at this point. So I think I should introduce the concept of software-defined networking, but I would like to first mention that there are two parts, two networks in an offshore wind. And the first one is this wide area network that I had mentioned, which serves that allows the control center and the cloud to communicate with our wind farm. So this one, the data that you transmit here is not very time sensitive or critical. But this one, it has very strict performance requirements because you want to make sure that you're able to communicate as swiftly as possible between the wind turbine generators and the offshore substation. Yeah, so I think I've mentioned this, that the challenge we have now is to ensure that we design and optimize the communication network that we have that section, and to ensure that it is robust, has low latency, quite reliable, and that it is secure. Yeah, I think I'd mentioned this, but I wanted to show it again so that you see how we deploy the devices, the networking equipment on both ends. So currently, how we deploy equipment is, assume you have a wind farm. I think I'd mentioned this last time. Let's take the case of an Anholt wind farm, which has 111 wind turbines. So what you find is that in this wind turbine, one of them, you could have about 5 switches, and a switch is what collects data. I think you had seen in a previous slide where we have a local data acquisition module. So what happens is when the sensors collect data, they send it to a local data acquisition module. Maybe let me go back to that slide. Yes, this one. So when we collect data from here, these sensors communicate to a local data acquisition module. But you could have more than one data acquisition module in a single wind turbine. So the communication between this and the offshore substation, here you have a switch. So a switch is a networking device that has a number of ports. I don't know whether we have one here, but a switch, it has could have 8, 24, or 48 ports. And in those ports, you will connect with a network cable. One will connect from the local data acquisition module into the switch. But some switches, or rather some sensors, are very advanced. So you could have a sensor itself has access to a switch. So you'd find that some sensors directly communicate to a switch. Now, moving back to the figure we had. Yes. So just a little math. If we had 100 wind turbines and each has 2, yes, each has like 2 switches. Just, assuming we have 2 switches per wind turbine, one which sits inside the, one which sits, yeah. So assuming this wind turbine has one switch, one at the tower, and two inside the nacelle. Just an example, assuming that one of the switches in the nacelle is the wind farm operator and the other one is for maybe the supplier. So let's say, give or take, every wind turbine has three. So if we're using the Anholt wind farm, we could probably have 330 switches in the wind farm alone. And then in the offshore substation, let's say we have like 20. So in total, we have 350 switches, right? I hope my math is right. So 350 switches, how we do it right now is you have to configure each and every device by itself. So that makes the work very tedious. And of course, you will also expose yourself to human error because as you configure, it's the same person. And usually you have like one person running the whole project. And maybe they have like 5 consultants working in the wind farm. So 5 people working with 350 switches, they are prone to make a lot of errors. And we don't have a way to know where the problem is until we start running our system. So in the current day, we are looking at how can we have better network and service management. So I want to introduce to you a concept called software-defined networking. And what we do with software-defined networking is, of the 350 switches that we had, we pull out the intelligence of all the switches and we put it in something we call a controller. So you will deploy your 350 switches, but they don't have any intelligence. And then you will have a controller seated somewhere, probably in the offshore substation. Of course, you don't deploy one, but we will see why later. And what you do is what you're seeing on your right. So you would have your switches, which is something we call an open switch, and it will communicate to an open flow controller. So now what we do is our engineers will go to the field and deploy the different switches, but then they will sit at the control center or in the offshore substation and configure everything from the controller and push it down. So we find that this technology or rather this approach will be much better and it's easier for us to send configuration and roll back if we have challenges in that configuration. So this is how an open flow switch looks like on the inside. As you can see, this is the ports that I was talking about where you connect. So this port, this is where you connect your local data acquisition system. And this you could connect to another switch. And then inside the switch, we deploy application interfaces that enable us to communicate not to one, but more than one controller. And I think when I talk about scalability, you see why it's important to have a connection to more than just one. And I'm sure you can already think of why it's important to connect to more than one. So what happens is the controller, as I'd mentioned, has visibility on the entire network. So it can tell that maybe the connection between one switch and another is off. So it disconnects. It could also tell if maybe a link has changed, the direction or the path has changed, and it will inform the switches in microseconds, and sometimes even in nanoseconds. Now, why this is interesting is because in the current topologies that we have or architectures that we have, it takes about, I think, 30 seconds to 5 minutes to have that information communicated. So we are seeing a lot of potential with this technology. Yeah, and also, I also thought to include this because this is for the wide area network bits, which I'm not going to really look at, but it also shows that it can be applied not only just between the wind turbine generators and the substation, but also between the substation and the control center or substation and the ISP. That's why you're seeing something called MPLS here. These are you communicate to an internet service provider. So we believe that sometime in the future, probably 2050 and beyond, we will see maybe a full implementation of SDN, or maybe in parts. But I believe it's going to be full because currently, if I may go back just a little bit, I had mentioned this, and most companies are already using SD1. And just to give you an example, if you're already using Google, you're already on the SD1 network because Google databases run on software-defined network. So we already see the potential here. What we are interested in is, can we also see the benefits of software-defined network on this side, where we have different performance requirements. So maybe just to also stay here a little bit, I like the example of Google because with Google, I think we have a lot of traffic, and we talk about a second, we send about 5 petabytes. I don't know, that is 10 to power. I don't know what it's 10 to power something, but it's quite high for it to be sent at this point. And that's with Google. And of course, the requirements for Google are different because if you don't get your video in about a minute, it's not a big deal. But for us here, if you don't send sensor data within the required time, or maybe control signals or protection signals, then you have a problem. So for us to design this section of the communication network with software-defined networking, we must guarantee that it actually works and that it meets all the performance requirements. So yeah, so for the sake of demonstration, as I mentioned, we have a subsea cable here. So you can imagine that this happens for all the different turbine generators. And then what you're seeing up here is what I was showing you in the offshore substation, where we have the virtualized PLC component and we have our edge computing here. So this is pretty much just a network diagram that shows you how we communicate both on the physical side and on the virtual side. And also something else to mention, and it's a question that we get often, is if you're deploying your SDN controller, doesn't your network become overwhelmed with control traffic, with scalability issues, etc.? So we will look at those and see the different challenges that we face and how we are able to solve them. Yes. So we singled out, okay, we said, fine, the architecture is very promising, but does the architecture face some challenges? So we were able to single out these four challenges, one being scalability, performance, reliability, and security. So looking at this architecture, I think the first question people ask is, if you're using, if you're bringing all the intelligence to a control center somewhere, doesn't it then become a single point of failure? So that's always the first question we ask. And how I answer it is that we hardly ever deploy a single controller. Yeah, I think we should be on this slide. Yes, so this part, we hardly ever deploy just one. We hardly ever just deploy one. So we often deploy a minimum of 3. That means you could have all the way to your 50s and 100s of SDN controllers. Now, what happens is you want these different controllers to communicate with each other and to also communicate with the switches at the substation. So how we design this? Oh yes, I think I did not also mention, another question you might ask is, how do you have access to the controller as the network engineer. And usually you use an IP address. So this is, I captured this from one of the experiments we've done, where you're able to insert an IP and you access the primary SDN controller. So, okay, let me then give you another scenario where we have three SDN controllers. As I'd mentioned before, let me go back to the, yes, I hope you remember this. So I said that in the open flow switch, you're able to connect to more than one controller. So in the architecture that I've just shown, assuming you're able to connect to more than one controller. So the first question you ask yourself is, which one should I listen to? So which one is the primary controller? So what we do, or rather the technology that is used is, assuming you have three SDN controllers, we use an algorithm called the Raft consensus algorithm to determine which of them will be the primary one. So this is a screenshot I captured from the algorithm running. And as you can see, the Raft algorithm begins by saying, okay, we have the three different SDNs in a cluster. And so it starts by saying, so here I was logged in to one of them, and you can see it transitioning from the state of follower to candidate to leader. So when it becomes a leader, it means that all the switches are looking to it for advice on how to forward packets. And then the remaining switches become either candidates or followers. So what happens if one of the controllers fail? The Raft algorithm does the same thing, and it makes the remaining controllers, one of them as a leader and the other one a follower. That way we ensure that we continuously have the network running properly. And worst case scenario is if all the controllers fail, what happens? So that's a question to answer later. Yes, so the other concern was about performance. So often, as I'd mentioned, is that, let me go back to this. Yeah, so to answer the question of performance, we look at what kind of data do we transfer between the wind turbine generators and the digital substation. So between these two, you can imagine we are already sending the different sensors, and that is what is represented in this table. Yeah, in this table. So this table captures the different data services that we send and how fast and how much volume of data we are able to transmit. So you can see like some of the most critical ones are below 1 second. So you have like 16 seconds for the analog measurements are mostly the sensor data. We then have also protection traffic. We have status information. We have control traffic. We have data calling. Yeah, internet connection is not such a big deal because it's just ensuring that when we have people on site, they'll have access to the internet, etc. So this table is able to help us determine or rather validate whether our system is working properly by observing how fast we're able to transmit data in our simulation environment. So when we talk about performance, when the network is operating properly, we always we will be transmitting data within the required time frame, or even in fewer seconds or microseconds. But our communication networks are constantly challenged in one way or another, which is what we are calling a stochastic disruption. Yeah. Now, stochastic disruptions could come in many forms. One, it could be that your devices are overheating and cannot send data anymore. It could be that maybe the marine life has knocked out one of the cables, subsea cables, and no longer have access or there's a link failure. And you can imagine of all the other challenges that you could have. For instance, you could also have your controllers failing. That's also a disruption. So I use this chart to show how the performance drops when we have that stochastic disruption. And as you can see, before anything happens, we're operating at full performance. Yeah. But when we have a disruption, we go down, so the performance drops. And then it takes us time to recover from the disruption. And how you recover from the disruption is using different techniques, which we're going to look at in part 2, to recover from this disruption. So with communication networks, of course, you will have a disruption. There's nothing you can do about the disruption, but it is up to you to determine how quickly you can recover from these disruptions once they occur. And now just to show you, this is an experiment we captured where we had switch failure. So at one point, our switch was transmitting data properly, but then our switch failed, and you can see how fast the data traffic stopped. So usually you can never have like a straight line because it's always internal movements of traffic, but you can already see what happens when you have a disruption. So this was a switch failure, meaning that the switch could not transmit data to the next device. And then we also noticed something else. So there's one point where you could have your switch completely fail, but you could also have your switch malfunction. So when it malfunctions, you can see that it just drops a little bit. So throughput is a feature that we use to monitor how much data has been transmitted. So here we tried to inject some failures into the switch just to see how it's going to perform. And we saw a decrease in the network throughput. So the switch was able to transmit some data, but not all the data. And then here you see us recovering the switch back to normal transmission. The other challenge is reliability. And reliability has a little bit also to do with the stochastic disruptions. And here we are saying what would happen if a switch fails, what would happen if a link fails, what would happen if the controller fails. So we got some data from a study done by Nokia Bell, where I think for a whole year, they were able to, so here I just captured for 5,000 hours, and we're able to observe how the survival rate, I think this was up to 29% only when we have disruptions. So here, what we need to do with our communication networks is ensure that we have availability and reliability. And this, I think, we measure with some metrics, I think, which Conrad will talk about later in the week. But some of the metrics that we use are maybe mean time to failure, mean time to recovery, and you also do an actual availability test to see how well it performs. And last but not least, security. And I think you'll also hear more about it in the week, that our networks are exposed to different vulnerabilities and different threats in different layers. For instance, when I showed you let me go back to the image we had for the controller. So if we are saying that this is where all our control or all our configurations are being done, what would happen if somebody intruded or had gained unauthorized access to our control plane? That would mean we would not have any data or any configurations being sent to our network, and that would pretty much paralyze the communication. So one other challenge, or rather another very important challenge, is to look at security components of communication networks and to ensure that we're able to, I don't know if you can go ahead of an intruder, but I always find that the best way is to look for all the vulnerability points and work around them before the intruder finds out. So these are the challenges that we find with software-defined networking. And in the next section, we're going to look at a performance challenge that we identified and how we solved it using reinforcement learning. So I will be taking any questions if there are any. To follow this session, if you're able to capture this QR code, it's a link to the website where it tells you step by step how we designed the, the Microsoft Azure testbed that I will discuss in part 2. However, you can simply listen in, but it's also nice to see it. And also the QR code has a link to all the other things that we spoke about in part 1. So if you want to go back to it, you will see it. Now in part 2, just to give a recap of what we did in part 1, we looked at what is the application scenario, how do we develop the communication networks, and what are the challenges that we anticipate with these communication networks. Now, in my work package, we have different researchers working on different things. So I thought to focus more on performance, which is what is most important for our communication networks, especially in the case of offshore wind farms, which is very critical. And in part 2, you will see some of the performance or other disruptions that we anticipate in our communication networks and how we are using reinforcement learning to sort of self-heal in a manner that we end up having an autonomous communication network. But first, let me describe all these buzzwords that I'm using. So one of, in communication networks, we have a standards body called the European Telecommunication Standards Institute, ETSI, and they come up with different frameworks to define how we look at performance and how we look at communication networks in general for all application scenarios. And recently, they came up with something we call a self-X network and service management framework that has 4 components, or rather 4 pillars. One being self-configuring. We want communication networks to configure themselves. We also want them to heal themselves if they encounter challenges. We want them to optimize themselves. And probably in future, we want them to protect themselves without human intervention. So for me, I took the self-healing because it's most interesting to me in the application scenario that I have. So you will see in this second phase of the presentation how we identify the challenges and how we heal them without involving a network engineer. So most of them would ask the question, so are you taking away our jobs with AI? But I would say no. What we are doing with AI is just ensuring that we help the network engineers do a better job and not take away their jobs, per se. So I will start by discussing how we designed the test bed, and we used a cloud-based system where we deployed our simulation platform on different virtual machines, which is we used Microsoft Azure. And what we did, I don't know, probably I should go back to the architecture of software-defined networks for us to remember how it was. Yes. So if you can remember from this architecture, we have the switches communicating with a controller. So we then demonstrated that with this setup. So here you can see the different switches on the wind turbine generators. Let me use a laser pointer. you can see the different switches. One you have at the nacelle and another one at the tower. And then you have L13, which is the subsea cable that communicates to the digital substation switches. And the switches are FD1 all the way to FD9. So those are the substation switches communicating with the different wind turbine generator switches. So this kind of setup is what you will see in the application scenario that we have in part 2. So just focus on the switches that you're seeing here, the FDs and the rack SDN controller. So let me go back to that. Yes, so if you look at this, let me zoom in to the different parts that I will find. Yes, so I will first look at this part. Yes, so the data plane is what we have as the devices that we were seeing in the offshore wind farm. So what we do is we use an emulator called Mininet to sort of mimic what we would have in an actual offshore wind farm case. So we have the different hosts that will be running Python scripts that send data, random data at different time frames, and they communicate. So we have the local data acquisition, as you can see here, which is what we had before. I think you can't zoom and yeah. So the local data acquisition communicating to a switch, and then it sends to something we call a spine leaf network. I think when you read from the website, you'll see why we opt for a spine leaf network and not the common network approaches. And then we then communicate to, yeah, let me zoom back in. Yeah, so you have the spine leaf network, and then here, this is now the substation where you have your merging units and your edge computing platforms, and you have some other devices that would mimic a sort of a control center for the on the substation where people are able to access the systems with a computer, etc. So we were able to develop this and run different Python scripts on the different hosts to send traffic through this switch network. And using tools like Wireshark, you can observe the traffic that is flowing, the time that it is spent communicating. So with the Azure, we used VM scale sets to ensure that we have enough redundancy so that the network does not fail, or rather the simulation setup does not fail. Then above, you can see the control plane, which is what we talked about. You deploy 3 or more controllers. Now, the interesting part is the part at the top where we develop different applications that we use to monitor the communication network. So as you can see, we have 4 applications that we've developed. One is the network monitoring module. We have a recommender module. We have another one that does predictive analytics. And we have the decision maker, which you'll now see how it does the self-healing. Now, just to move forward, I think this shows you. Yes, so this is what I meant by the traffic generation. So we used the table that I had shown you before, where we're able to transmit both time-sensitive and best effort data traffic through the data plane. So why is it important for us to self-heal? I had mentioned before that there are some challenges that could affect the control plane, and there are some challenges that could affect the data plane. So the control plane, as we had mentioned, it's deployed as virtual machines. So you could have controller 1 is a virtual machine, controller 2 is another virtual machine, etc. So you could have n virtual machines running on either one server or different servers. So if you send a lot of data samples and the controller has to keep checking how to forward those data packets, you might find that you will consume a lot of CPU and memory. And then, given that you're using virtual machines, it is possible that a virtual machine could crash. So there are questions we're asking: how can you recover from this, and how can you detect some of these challenges? Now, on the data plane, there are also challenges that you'd expect. For instance, as I'd mentioned, something like L13, you could find that maybe a shark has hit the fiber cable and it's broken. What do you do? You could find that a normal link has failed. What do you do? You could find that a switch is probably overheating or it has failed to perform. So you ask yourself, what do we do about this to ensure that we continue to have high network performance? So I developed this framework that would help us, one, observe, and two, observe, troubleshoot, and heal the network autonomously without involving the network engineers. So what we do, remember the control plane has access to the entire network, and we're able to see everything across the entire wind farm. So we used REST APIs to capture different metrics and send them to the knowledge plane. And then from the knowledge plane, we run reinforcement learning to help us decide on what to do based on the data that we have. So I will take you step by step. We have 4 modules in our knowledge plane. I will show you what each module does. And then we will see how the reinforcement learning actually helps us do the self-healing. Yeah, but also before I move forward, we have another section here called an abstraction module. And in our knowledge plane, you will find that we're using some thresholds much later in the discussion. And we often get those thresholds from the O&M team and the different regulators, etc. So you will see that in the following slides. So the first thing that we do is to observe our network. So observing means we determine which metrics we are going to capture from our control plane. We probably want to see how is the CPU being consumed. We want to see how much memory is being consumed. We want to see which links are up, which ones are down. So when the state of the link changes from up to down, that's how you know that a link is broken, a link is working. Then you also want to monitor, is the switch performing well? There are some metrics you're able to pull. So this schematic that we have here shows the internal process of the controller and how we're able to capture the information using a RESTful API script. Now, when we capture that data, we put it in a database somewhere, and we're able to read that database to either have visualization, if you want to do predictive analytics, or forecasting, or whatever you want to do. So you can see here we're using Grafana to do the visualization, or you could use any other third-party analyzer. Now, the reason why we chose InfluxDB, it's because it's a time series database. So when you put the data into the DB, it automatically shows you the graphical output, so you don't have to run so many queries in that database. Now, now this is the intelligent part of the self-healing algorithm. So what exactly did we do? As I'd mentioned, using RESTful API, we were able to gather a lot of different metrics, but then we had to narrow down to what is very important for us to use. So for us in the application scenario of an offshore wind farm, we want to make sure that we transmit data within the time latency requirements, maybe stipulated by the different standards. And we also want to monitor the health of the devices in the network. So we designed, so this is just a snapshot of what we were able to pull from the controller using the RESTful APIs. Now, we looked at the simulation setup that we had, and we had the links that we used. I think if you can remember the figure that I had before, I think I can look at, let me go to, yes, if you look at this figure, when I talk about a link, I'm talking about these numbers, which are from L1 to L13. So that's what I'm calling a link. And then when I talk about devices, it's the different switches that you can see here. So these devices that are connected by the links. So when I'm communicating probably from this wind turbine to this FD9, we use something we call a path. So your traffic will pass through a number of devices all the way to the end. So it is important that all those devices on that path be working properly and the links to also not be overloaded. So if the path that you've chosen is congested, then you will have challenges meeting the latency requirements that are stipulated for whatever wind service that you're using. So let me just go back to what we had in the self-healing framework. So yeah, so here, what was very important for us to look at was what are the path latencies? And then we also wanted to look at, for all those links, how much has it consumed? So like if we're transmitting a lot of data, how much of that link is being consumed? Is it 80%? Is it more than that? And then in my network, I had about 40 switches that I was using. So as you can see here, we did a computation, and so that our state space would have 178 elements, which was workable to use as an input. Now, anybody can retrieve this data, but why is it important for us to do this in a self-healing kind of framework? So what we did was to use, if you remember, I mentioned something called like an abstract module. So the abstract module, let me go back to that. Yes, this one. So this abstract module, what happens in offshore wind farm data transmission is we say, we want to make sure that if you send a goose message or an SV, it should go within this time. If our network is operating, we expect it to be up 99% of the time. So we give all these different thresholds to ensure that our network performs optimally. So if our network violates any of those thresholds, then we have a problem and we need to look at what is the challenge and correct that. So in my framework, I looked at the application scenario I had, and I thought, what is important for me to consider as a violation? So based on the state space, we got three normalized thresholds. One, we were saying for every link that connects one switch to another, we want to make sure that that link should not be consumed above 80%. Also, we were saying between one source device and a destination device, that the path latency should not be above 3 milliseconds. And then, given that we are in an offshore environment, we expect that our switches will be overheating, etc. So we looked at the guidelines for data centers and said, what is the optimal temperature for data centers? So we got that our devices should always be operating between 18 and 27. And when we looked at the temperatures that we see even in our offshore wind farms, we noticed that some switches go up to even 35, even 40. So that is a problem, because if a switch is overheating, it means it can have a lot of packet drops, and we don't want to have that. So we monitor our network So when we pull these values that we have in the state space, we run them through a violation checker to check whether it meets, it violates any of these. And violation here, we use the logical OR, because if it violates the link utilization, then we have a problem, instead of considering all of them at once. So we fed the data that we collected into, yes, and this is what I was mentioning, that if we have any of the violations, you notice loss of datagrams, and we were able to detect up to 5.27% in terms of loss, which was pretty much high, because that means you would lose a lot of control and protection traffic that's flowing. Yes, so we fed the data into a deep neural network. I think we had 3 inputs, as you can see from the state space. You have the path latencies, link utilization, and the device temperatures, which is the tau you're seeing here. And we fed that into a deep neural network for it to decide for us. And some of the decisions that we want to make are, I will go back to this. Yeah, to this topology. I think I should go back to this one for the traffic generation. If you look at this topology, you can see between one wind turbine generator and maybe an ECP, there are so many paths you can use to get to this end device. So what we want to make sure is that if in the path that was already selected, the switch is overheating, our self-healing framework can quickly choose another path and we reroute traffic through another way. And how we will measure how effective this module is to compare it with some baseline algorithms, and to also look at whether we lose any packets during that transition. So we did that, and then let me just go back to, yeah, so we were able to choose to make decisions based on this action space. So we're able to choose which is the best path to route our traffic. And if maybe we've consumed, maybe like the link utilization is probably up to 95%, we will allow only the important traffic to go through and maybe hold off the remaining traffic. So this is the decision that we made. We either reroute traffic, as you can see here, we either reroute traffic on the redundant paths, or we throttle the low priority traffic. So we were able to achieve that, and see what you can see on the right is a caption of how we were able to make the decisions. And lastly, once a decision is made, we are able to send it back to the network and say, if you send your data through this route, it's going to transmit packets without any loss. So we used, yeah, so this is the graph that we observed from the control plane, which gave us values that could show us that we've inserted new rules that will allow you to communicate much better and much more effectively. So in a nutshell, the main goal of this application was to say, okay, we would expect that in as much as this technology has its benefits, we still expect that it has challenges. And is there a way we can use AI to autonomously deal with these challenges so that network engineers can focus on better tasks? So that is all I had for today, and you can have access to more of our materials and probably a step-by-step approach on how to create the testbed if you're interested in telecommunications. Yeah, the repository I think is open access. No, it's public, so feel free to fork it if you have a GitHub account. Thank you. That's all I had for today.